Hello everyone. In today's class, we are going to apply everything we have learned in this first module of fundamentals of point kinematics. Remember that kinematics studies the motion of objects without taking into account the cause that produces it. In motion, these three vectors, the position vector, the velocity vector, and the acceleration vector, completely define the motion from the kinematic perspective. With these three vectors, we can calculate other physical quantities. For example, instantaneous speed is calculated as the magnitude of the velocity vector. From the instantaneous speed integrating, I can obtain the relationship between the path s traveled along the trajectory and the elapsed time t. From the instantaneous speed, I can also calculate the tangential acceleration as the derivative of the magnitude of the velocity with respect to time. If I calculate the magnitude of the acceleration vector, with this the tangential acceleration, I can calculate the normal acceleration. Finally, with the magnitude of the velocity and the normal acceleration, I can calculate the radius of curvature ρ at each instant of time. Well, let's calculate all these physical quantities in a practical example. Amanda is observing Jay in one of his training sessions. She tells us that the position of the ball is given by the position vector we see on the screen. And we are asked to draw the trajectory of the ball, calculate the instantaneous velocity, the instantaneous speed, the acceleration vector, its components, the tangential and the normal, and finally the radius of curvature. But the first thing we need is a reference system. We have chosen some Cartesian axes x and z, at whose origin Amanda is observing the movement. Specifically, it is a parabolic shot that runs in a plane parallel to the y-z plane, specifically 4 meters behind Amanda. Therefore, in the position vector, we see that the x component is constant and equal to -4. To obtain the trajectory of the ball as requested, we are going to give values to the time. And we are going to obtain for each instant of time the x and z components of the position vector. At the initial instant, the ball is in the hands of J, and we can observe that its height, its z component at that instant of time is about 2 meters. At the next instant of time, at 0.2, the y component is 1.09 and the z component is 3.1. If we go to the graph and represent these values, we obtain this point of the trajectory. At the next instant of time, the y component is worth 2.18 and the z component is 3.81, which corresponds to this other point on the trajectory. And so on until the ball reaches the basket. At that instant of time, the height is about 3 meters. We can also observe that the maximum height that the ball reaches is about 4 meters 15. Next, we are going to calculate the velocity vector as the derivative of the position vector with respect to time. We thus obtain another vector that also depends on time. Given values to the variable t, we can obtain the x, y, and z components of the velocity vector that will allow us to represent graphically the velocity vector at different points of the trajectory. We note that this vector is tangent at all times to the trajectory, that its x component at all times is 0, because, as we said before, the movement takes place in a plane parallel to the y-z plane, that the y component, the horizontal component, is constant, and what varies is the vertical component, the z component. At the initial instant, this component is maximum. At the instant of maximum height, we see that it is 0. We can observe that the velocity vector is completely horizontal, and then becomes negative, since we see that the velocity vector has changed direction. At this moment, it goes downward. Let us now calculate the instantaneous speed as the magnitude of that velocity vector we just calculated. The magnitude of a vector is calculated as the square root of its component squared. We have obtained an expression that also depends on time, giving values to t, and we obtain the instantaneous speed at different instants of time. This instantaneous speed corresponds to the length of the velocity vector that we have previously represented. We can observe that at the initial instant, the instantaneous speed is maximum. Then it decreases until it reaches its minimum at the point of maximum height, and then increases again. Next, we are going to calculate the acceleration vector by deriving the velocity vector that we have already calculated. We obtain a new vector that has only the z component. Specifically, it is vertical and downward, and its modulus corresponds to the acceleration of gravity, with that 9.8 that we all know. Let us now calculate the components of the acceleration vector. The tangential component is the derivative of the velocity magnitude with respect to time. If we derive this expression, we obtain an expression as a function of t. Given values to t, I obtain the different values of the tangential acceleration. I can observe that at the beginning this tangential acceleration is negative. If I look at this point of the trajectory, this is the total acceleration vector, which we have said was vertical and downward. And if I decompose it into tangential component and normal component, I see that the tangential acceleration is negative, since it goes in the opposite direction to that of the movement. At the point of maximum height, the tangential acceleration is 0, all the acceleration is normal. And from that instant of time, the tangential acceleration becomes positive. If we focus on this point of the trajectory, this is the total acceleration, this vector. We decompose it into tangential acceleration and normal acceleration, and we see that now the tangential component has the same direction as the movement and therefore is positive. We will now calculate the normal acceleration as the square root of the magnitude of the acceleration squared minus the tangential acceleration squared. From the values of the acceleration and the tangential acceleration, I calculate the different values of the normal acceleration. We can observe that the normal acceleration is increasing until it reaches the point of maximum altitude and then decreases again. Finally, we will calculate the radius of curvature as the magnitude of the velocity squared divided by the normal acceleration. From the values of the velocity and the normal acceleration, I obtain the radius of curvature at different instants of time. I can observe that at the beginning this radius of curvature is large. For example, at this instant of time, this is the circumference that best fits the trajectory at that point. Then it goes decreasing. We see that at that point of maximum height, this is the circumference that best fits the trajectory. Then it goes back and increases again. In this table, we see all the physical magnitudes related to the calculations in this practical example, which I hope you have enjoyed. See you soon.